keep this one. Okay, so first of all, thanks for the organizer for inviting me on this talk. Is it working? Okay. Yeah. So I'm gonna try to give you a bit of overview of what we can do in terms of cosmology with gravitational waves, going through the methods, showing, let's say, the current state, and then a bit of future perspectives. So the main idea, well, let's go through the methods first. The main idea is how do we go from here, so waveform, do we have a pointer? Yeah, from the waveform to basically infer how the universe is expanding. First of all, from the waveform, we can get the most important parameters for cosmology, which is the distance to the source. This is something that we get for free. And we basically do parameter estimation on any signal that we receive from, let's say, compact binary collections. And we extract the distance to the source, the luminosity distance to the source. Once we have this, of course, before going to do it, the most important thing is this is a measurement which does not depend on the cosmic distance ladder. It's a measurement of cosmic distances, but it's an absolute distance indicator in the sense that if you believe general relativity, sorry, Chris, it's unbiased in the sense that does not depend on other measurements and so on. Which means that assuming you have also measurement of redshifts, what you can do is fit the usual distance redshift relations and get out statistically constraints on the cosmological parameters. If you are used to what supernova do, this is exactly the same thing. The main difference is that with gravitational waves, we have the luminosity distance for free, but we will struggle to get the redshift. With supernova, it's the other way around. We get the redshift almost for free, but we need a bit of work to get the luminosity distance. So how do we get the redshift? This is the main point. We get distance from gravitational wave source. We need a redshift measurement to do cosmology. Well, there are three main methodologies that we can use nowadays, and they are nicely summarized on what they call the standard siren pyramid. So standard sirens is just a terminology that is equivalent to standard candles because gravitational waves are distance indicators. So we call them standard sirens with the analogy between light and sound. And the standard siren pyramid, it works like this. So on the x-axis, you have actually the number of effective gravitational wave sources you can see. And on the y-axis, you have the information that you use to localize your gravitational wave sources. On the top, you have gravitational wave sources with counterparts. There are not many. We have just one for the moment. But we use a lot of information from electromagnetic observation because we localize perfectly the source. On the bottom, we have almost all gravitational wave sources we can detect, and we can use methods, statistical methods to get out cosmology. I'm going to introduce that. And in the middle, of course, we have what we call these dark siren statistical methods, where we use basically galaxy catalogs to get some information on the possible localization of the source. And in the following, I will use this notation that you can see here to basically, whenever I talk about something in my slides, you can recognize if I'm using any of these methods by basically the color that you see on the pyramid. So red means I'm not using that method. Green means I'm using that method. So let's see if this works immediately. So the first standard sirens that we have is the best one and still dominating our measurement of cosmology is, of course, GW17 or A17. As you can see, we only use counterpart, so first method. How does it work? Well, this is straightforward. You get a gravitational wave event. You go and look in the sky localization region. Very important to have 3 detectors, as you can see from this plot. If you have a mechanism to generate a counterpart, you might be able to see one. This was exactly the case of GW17 or A17 here, which basically produced a gamma ray burst in less than 2 seconds after the gravitational wave merger, and then of course, we saw the kilonova with subsequent observations. Once you get counterpart, you measure the redshift from the host galaxy, and then you have 1 point. I don't have it here. Well, we have 1 point on the distance redshift diagram that you can easily fit and get your cosmological constraint. If you don't get a counterpart, you have the second method here. And the idea is the following. You still go and look in the sky localization region of your gravitational wave event. You take a galaxy catalogs, and then you assign to each of this galaxy a probability that it's your host. I mean, it's the host of your gravitational wave event. If you're lucky, you have few galaxies. If you're unlucky, basically, you have a lot of galaxies. You cannot get much information. Each of these galaxies will give you a measurement of redshift, which basically translates to a measurement of Hubble constant of any cosmological parameter you want to infer. So the idea is that you take these measurements and you stack them. Of course, if you have one event, you may have a situation like this one, where basically all of your galaxies are clustered here, but your true galaxy is here, so you're completely biased. So you should never use this method with just one event. But as you add events, for example, now with 15 events, it's a simple simulation created by Varte Depot, so with subsequent, let's say, GW17 or 17 similar detection. With 15 events, for example, you start to see that you see the true value in this forest, however, still very, very uncertain. Once you go to, let's say, 30 events or more, then the statistical measurement of H0 comes out easy statistically. This is why, let's say, if your galaxy catalog is complete in the region you're looking, then the host galaxies is always there. So we always give you the measurement of H0. So and all the other galaxies will give you spurious measurement. When you stack events together, the one true measurement is always there. So it's piling up, and the other ones are basically washed out. Easy to understand. Now comes a difficult part. So this is the third method. Still look at the little symbol on the top. This doesn't require any electromagnetic informations. And the idea is the following one. This nice picture created by Vasco that will be uptold just after me. If you have a mass distribution of your gravitational waves population, let's say binary black holes, but this works for any population you have, at the source frame, so with no cosmology, that looks like this. In the detector frames will be basically modified by the fact that you have that all masses that are shifted at the detector frame. So everything gets shifted this way. So the idea is the following. If you have a source frame distribution and a detector frame distribution, you basically statistically try to reconnect the detected distribution to the distribution at the source. I'll say source frame distribution. Of course, this can only be done if you have a model for the source frame distribution. So suppose you have a model like this one that was used for the O3 analysis. So this is like, this one was the best one, let's say. So a power law plus a Gaussian peak. That's how your masses are distributed in the detector. You have some parameters that describes this model. And then you fit these parameters together with cosmology. So you can get some interesting cosmological constraints. This is very hard to explain in 2 slides. So Vasco will be able to do this better after me. Okay, there are other methods that I'm not going to discuss because they are, let's say, less relevant, at least today. They will be maybe more important with 3G detectors. Of course, lensing, if you get lensed sources, you might be able to detect constrain cosmological parameters for the time delay between the images. You can use the tidal deformability of neutron stars to decouple basically masses and redshift and so on. All these effects are very useful, let's say, in the future, but nowadays we cannot use them. So let's go to current results. I'm not going to go through that. You should all know that we have 4 detectors nowadays, and we will have some more in the future. This is the current status of detection, of detectors or observations, let's say. The main thing I want to point out here is that starting from O3, the rate of detection jumped a lot, which means that it's here when we started really to population analysis, and also for cosmology, this changes things. So the first results we got, and the best one still, is GW17 as I said before. By taking the measurement, redshift measurement from the host galaxies that we identified through the counterpart, we got a constraint which is at the level of, let's say, around 20% on H0. This is not compatible, sorry, not competitive with the standard electromagnetic observation like CMB and supernovae, but is a compatible measurement, as you can see here. And in the future, hopefully, we will have more counterpart, and this will go down hopefully to the precision of H0. I will show you when in a moment. I will skip this slide. The only important thing here is that GW17 was quite close, so basically we only could fit H0, and we couldn't basically fit any other cosmological parameter. An important thing that I would like to point out, especially for people in the audience, is that if you add electromagnetic information on the kilonova and so on, you can actually improve cosmological measurements. So this nice paper here showed that by modeling the jet emission from GW17, you can actually get constraints on the emission angle of the jet, which is correlated to the polarization angle of the binary system. And this is very important for cosmology because there is a strong correlation between distance and the inclination angle of your system, which directly translate to the measurement of H0. But if you assume basically the Hubble law, this is just the distance. And you can see here that there is strong degeneracy. You can see it also here, that you can basically break once you add information from the electromagnetic kilonova. This, of course, it's very nice, but it depends on your model for the kilonova and so on. So it adds possible systematics and so on. I'm going to skip this slide because Chris already talked about that. So we constrain the speed of light with W17 and 17 up to the 10 to the 15 level. And I'm going to the statistical dark science method using galaxy catalogs. So this was applied to O2 results for the first time, and then to all O3 results after the O3 observational run. At the moment, as you can see, well, here, but yeah, maybe, well, here you can see. So here, basically, in O2, there's basically no information from statistical dark siren. We are basically dominated by GW17 and 17. In O3, we are starting to arrive at kind of the same constraint, but these kind of results were fixing the population model. So we were not inferring at the same time parameters of the population and cosmology. So it was very optimized results. As you can see here, is red. So we're going to do the results. We're going to show you the results in a minute that we updated with the full fit. But the most important thing I want to discuss is that for this method, the very important thing you have to keep in mind is that your galaxy catalog will never be complete. So there is one important thing you have to address is incompleteness of the galaxy catalogs. And this picture that I took from one of the LDK paper show it really well. This is the Glade catalog that Gergely will present tomorrow. And it's the one that is used for the analysis in O2 and O3. You see, it's basically after redshift 1.1 it's not complete, it's less complete than 50%. If you use another catalog like DES, then you can find this analysis much further. However, DES, you need to be lucky and be in the field of view of DES, of course, to see this, but that's very important. So, see it also by Gergely tomorrow. He will explain all of this. So the last method, the one not using any electromagnetic information, was again applied to O3 data. And I don't remember if we had the analysis for O2, but I don't think so. We didn't have a pipeline LVK for O2, but for O3, yes. The measurement of H0, I mean, it's just a little improvement over O2 results. This includes also the W17 and 17. So is this basically this measurement? The main important thing, you can see that the measurement without including W17 or 17 is quite broad, and it's very dependent on the mass model that you use. So if you have the wrong mass model, you will have a big bias on your H0. If you have the right mass model, of course, you will have no bias, but nobody knows the right model a priori. So you really need to try different models and be sure that it's not affecting your analysis. And here we fitted also for omega m and equation of Taylor Kennedy. As you can see, basically our results are, we don't measure anything. So finally, we put everything together. This was post 04. Sorry, post 04. I'm not in the future yet. Post 03. What we did as a major update in the cosmology working group of the LVK is basically put all the methods together into a single pipeline. Now we have two pipelines that actually we're going to be used for 04 that put all the information together. So you can see that it's all green here. And we already tested them on the results of 03. What you get is basically same results, more or less, that we got from the LVK from 03, but now we are fitting also for the population parameters. So this includes a fit on all the population parameters. And as you can see here, actually, by including this fit, the posterior broaden a bit, and we are still dominated by GW17 and S17, but in any case, adding the information from dark siren, let's say, we still add a 20% improvement on the measurement of H0. What we expect at some point, maybe 04, maybe 05, if we don't detect more counterparts, dark siren will become more constraining than GW17 and 17 eventually. So future prospects. Didn't see any signs, so I'm assuming I'm doing good with time. Okay. So I stole this picture from a talk by Archesman, which is really nice. I just changed it. He was putting 2028 here and 20. Too optimistic. I just put some question marks. So what we want to do with this? Of course, you know there is a big problem in cosmology, which is H0 tension, or Hubble tension. The measurement from supernova, or let's say local distance ladder, are very different from the measurement coming from CMB. So this tension is now like 5 sigma or more. A gravitational wave, of course, can give an independent measurement and possibly solve this problem. What we have today is, of course, not comparable with what we have with the EM observation, but the question is when we will be here, let's say at the same level. Just mentioned here, you can see that the LVK results are a bit more optimistic with respect to what we have nowadays, because we are not fitting for the population parameters. Here again, we are fitting for the population parameter. Okay, I found this paper. I think Weizmann is in the room. It was a nice analysis of what we can get in 04 and 05, also with counterparts and so on. And I think it's one of the most recent ones. Showing that with the electromagnetic counterparts, if we expect, let's say, to see, let's say, few counterparts, or let's say up to 8 counterparts in 05 or few in 04, it's going to be very hard to arrive to few percent on H0. So even only in the very, very optimistic case, let's say 05, and we get down to 7, 8 counterparts, then we are at the level of let's say Planck and Schuss. This doesn't account, of course, possible systematics on the level of accuracy on the waveform, calibration of the detectors, and so on. This must be taken into account. Will be very relevant once we reach the percent level, but we are not there, so everybody ignore them. Once we will be there, this will be very important. But the bottom line is that few percent accuracy on H0 is probably not going to happen before the end of 04. However, things are changing very rapidly in GW cosmology. There are new methodology, new ideas, and new results, new data also that are being used. I will not be surprised that at the end of O5 we have a few percent measurement, let's say, of HO. Forget about O4. O4 will give some new updates, very important, but we will not solve the Hubble tension with O4. These are the forecasts regarding dark sirens found also on this paper, nice paper by Nicola Borghi collaborators. This is very optimistic because they were basically assuming that the galaxy catalog is complete. They were making simplified analysis. They were considering full 5 detectors, including also LIGO India. No, not LIGO India, but cadre that works at, let's say, 120 megaparsec. Very, very optimistic. But still, it's nice results, at least. You can see that with spectral sirens, this is what we call when we never use electromagnetic information, we can get basically down in O5 almost to, what is this, 30%, just without electromagnetic information. And if we have galaxy catalogs fairly complete, we can really go down below 10%. This is never going to happen. We will never have a galaxy catalog, spectroscopic galaxy catalog complete up to redshift 1 in 10 years. I don't even know if we will have it in 20 years. This might be realistic. Let's say that the truth will be probably around these values, probably around between these and these values. So you can see that actually we might arrive 10% after O5, maybe a bit more if we are lucky, but we will not be at the, let's say, 2-3% level of Planck and so on. Okay. This was for current detectors. Let's go even more in the future. We will have Einstein telescope and cosmic explorer, hopefully. 10, well, order 10, on one order of magnitude improvement with respect to current detectors. And of course, with these kind of things, you can do what I would call precision gravitational wave cosmology. So here are some of the recent analysis. So for bright sirens, assuming, I think these results assume Vera Rubin Observatory to look for counterparts. You can actually see that you get to really below 1% or below on the Hubble constant, just with 1 year of observation in ET and Cosmic Explorer. Of course, it's going to be hard to measure omega m because you measure the majority of counterparts, you measure them at low redshift, so you don't measure higher order, let's say, parameters. But if you combine with the Planck or whatever EM observation, then you get, of course, a better measurement. And we will start also to constraining dark energy, very relevant nowadays. Might not be relevant anymore in a few years, but we will get some constraint. Of course, these are not at the level of what we get even today with DAISY, but this is based only on counterparts, so we don't have an analysis yet for everything together. For galaxy catalogs, this is something we did a couple of years ago. You can get, again, down to few percent. This is not without any counterpart, but assuming that you have a galaxy catalog complete up to redshift 1, let's say, or more or less 1. Photometric. We're not considering spectroscopy. And finally, this is the spectral siren method. So no electromagnetic use. This is a nice new paper, actually still under review, that came out a couple of months ago. I think it's the only spectral siren analysis that I found so far for ET and Cosmic Explorer. You can see that depending on how many sources you use, so you can cut, this is the cut in SNR that you can use. Of course, you can constrain this down to very, well, this is probably 10% or something, but if you use the whole sources, probably you can go down to a few percent. It's an interesting result in the sense that assuming that we have a good model for the mass binary black holes mass population that is not biased and so on, and assuming that there are enough features in this population, we will get 2% or whatever percent in H naught with the 3G independent of electromagnetic counterpart. Okay. Of course, if you get electromagnetic counterpart, it's much better, but this is guaranteed, assuming we know the model. This is still preliminary. I'm expecting more analysis in the future, but we will see how it evolves. And finally, as I was mentioning before, this new method, this alternative method that you can use actually the equation state of the neutron star to basically break the degeneracy between the mass and the redshift. There were some analyses in the last few years about this. You basically cannot use it with current detectors because you don't have a good measurement of the equation state of the neutron star, but with 3G you will have it. So you can use it also to make cosmology. And again, you can go down to a few percent with this, but this is assuming that you can model really well the equation state of neutron stars. And then you assume that the equation state is the same for each neutron star. So it's a bit assumption, but you can extend this analysis by, let's say, taking a population of, or like taking a hyper distribution of neutron stars parameter, equation state parameters, and so on. Nobody did it yet, but one can do it, and I guess results will not be much different than this, because we communicate with this kind of detector, we see every parameter really precisely of the binary. And finally, we can go for LISA in the last 2-3 minutes that I left. No need to explain what LISA here, so just go fast here. The only thing I want to point out here is this: there is a big white paper on cosmology. So if you want more information on cosmology with LISA, go there. There is everything. Came out a couple of years ago, 3 years ago. So it's quite recent. But what are the cosmological sources we can use for LISA? So everything that we can detect at cosmological distances, we can use it for cosmology. This is the main message. Stellar mass black hole, intermediate mass black holes, if they are there, but especially MRIs and massive black hole binaries. So let me go through there and tell you why I crossed out stellar mass black holes and why this question mark here and so on. So stellar mass black holes, they were very promising 10 years ago when we believed the LISA could detect hundreds of them. With the new sensitivity and new analysis, we detect basically just a handful of them. So it means that we cannot do really cosmology, unfortunately. However, if they are, I mean, if there is a population of more massive black holes, say intermediate mass black holes, hundreds of solar masses, between 100 and 1,000 solar masses, this will be perfect multi-band binaries, assuming you can see them with ET, or they merge in ET, let's say. And with this, you can really do cosmology. Right? With just 10, order 10 multi-band sources, you will be able to get H naught at 2%, as we show in this paper a few years ago. Another source, very important, is MRIs. So MRIs are quite interesting. You can detect them up to redshift 4. They are not in we are not expecting any electromagnetic counterparts, but there are some models that can tell you that there is a counterparts, but I didn't see an analysis, a convincing analysis that this can be detected in big numbers so far. Detection are still uncertain, from 1 to 1,000 per year, but the ones that are useful for cosmology, which means well localized, basically, are, let's say, 1 to 100, depending on the models, on the population models. With this, you can get H naught between 1 and 10%, again, depending on the rate, without using electromagnetic info, right, without using a galaxy catalog, say so. Yeah. Remember, whenever I talk about anything, just look at here with the method that I'm using. And we can also start to probing the equation of state of dark energy. If we get an MRI which is lensed, in the best case scenario, say we see 1,000 per year, one of them might be lensed. If it's lensed, we will have a very good scale localization. We can get the galaxy. We get the galaxy with basically a counterpart. One of that, we get H naught at 1%. Assuming, of course, all the cosmological parameters are fixed, because with one event, you can just infer one parameter. It's not that you can infer many parameters. And finally, massive black holes. These are the most interesting sources for LISA because you detect them at really high redshift, up to 20, if there is any there. We might expect counterparts from them. people talk about this in the workshop, but still uncertain how many and how and why. But let's say we see, let's say 1 to 100 of these massive black holes. We get the best localized one. In the exercise we did in this couple of papers, we see that we can get between 1 and 5 counterparts per year, or less. 5 is very optimistic, 1 is realistic. But with this, we can do precise high redshift cosmology, which means these are the numbers that we get in this paper. I said this is more realistic, this is a bit optimistic. And you can see we can detect them up to redshift 3, let's say. It's really interesting. And well, depending on the population of the massive black holes. But the most interesting things, what I call precise high red cosmology, with this we can basically constrain the, well, this is H naught and omega n, but this is the Hubble parameter, let's say the constraint the hub H of Z at Z2 or 3 around the 10% level. So this high redshift, let's say, cosmography is not few percent, but I assure you that a measurement of the expansion rate of the universe at redshift 2 or 3 or about 10%, you will not see it from other sources, I mean, not soon. And finally, final slide. I am just putting here what we can get if you put everything together for LISA. This is something we still have to do. It's probably 10 years. I don't know, 5 years I showed these slides and saying we are doing the analysis. I thought it was really easy at the beginning. We just put together everything. No, because we're putting together different populations with very different masses, very different redshift and so on. It's not trivial at all. So we're still doing the analysis, but it should be ready soon. Then Ilagi is one is now in charge of this work. If you put them together, actually, the nice thing is that massive black holes at high redshift and MRIs at low redshift will nicely combine in the lambda-CDM diagram to break the generacies and basically get really good constraints on cosmological parameters. What I'm expecting to get H naught at the 1% or even better than 1% level with this modulo systematics and so on. Okay, this just a summary for LISA. Bottom line, putting everything together, we might get down to 1%, and I leave you with my conclusion, and I'm sorry if I'm late.
Thank you very much. We have time for questions. Yeah.
Thanks, Nicola, for the great overview. A question on the spectral siren. The mass function of stellar-sized black holes is still something that we are working on. So especially its dependence with redshift. None of the models I'm aware of predict a strong dependence with redshift of the mass function, but nature can surprise us. So is there some study using instead the binaries with neutron stars? Because the neutron stars masses are way more reliable as a spectral siren.
Yeah, you can do the same analysis with the neutron star.
Has it been done?
It has been done. It has not been done by the LVK because the problem is we don't have many neutron stars so far. So yeah, we don't have much information from there. But there are forecasts and so on that use neutron star with in the same way. You basically have a mass distribution from the neutron star. It might be, I don't know, a Gaussian or whatever. And then you try to infer cosmology. Actually, the first method, the first ideas for this spectral siren method came from neutron star because we thought neutron star are all 1.4 solar masses, so just put a delta function, you can measure cosmology perfectly. That was the idea. But of course, this was very idealized, but it still comes from there. The idea is the same, it's just instead of having a delta function, you have a distribution which is much more broader. The important thing is that you have some features in the distribution. Because if the distribution is flat, even if you have cosmology, it's just translated, but basically you don't have any anchor in your distribution to know where are the...
Well, it's more or less a delta function. the mass of neutron stars is more or less a delta function compared to black holes.
Right, compared to black holes, yeah, for sure.
Thanks.
Yeah.
A few years ago, Tim Dietrich and colleagues of him, they put out a constraint which was much better than the one which you have shown from the neutron star merger, and they combined all sorts of data. I think I guess everything together, the electromagnetic information plus the GW, but also I think equation of state data. And it was half or better than from what you showed. Can you comment?
Was it based on real data or was a forecast for the future?
No, this was based on the gravity. I think that was the neutron star merger that was observed. We evaluated, with essentially, I don't know, probably a Bayesian framework and throwing in everything we know. But it was really, much better than what you have shown here.
Yeah, knowing Tim, probably they model the counterpart emission and the kilonova through, let's say, numerical simulation. And they did something similar to here. So if you use information from the counterpart on the kilonova emission, and basically the main information is from the angle of the jet, you can get better constraints than the one we get only from gravitational waves. I guess they did another, I don't know the paper you're referring to, but I guess did a similar analysis. And of course, they get better constraints from what you get from the LVK. But this relies on more EM information that comes from outside gravitational waves and on the modeling of your electromagnetic emission.
And do you think the modeling is robust or is it dangerous?
That's hard to say. We have one event, and once we get few of them, we can check for systematics and so on. I'm not an expert on electromagnetic, on kilonovas and gamma ray bursts and electromagnetic emission for gravitational waves, so cannot say if it's robust enough. What I'm saying, statistically, I will wait for having at least a few of them to check.
Other questions? Yeah.
Actually, just a quick comment on this very point. Talking about systematics of electromagnetic counterparts. So there was recently a paper by Michael Müller and Shubhadeep Mukherjee, I think, pointing out that this result from GW17 or 17 could actually, in fact, be much worse if you relax the assumption about the jet orientation, right? So because we fundamentally don't know whether the jet is perfectly aligned with sort of the orbital angular momentum axis of the system, and so they were basically showing if the jet direction just differs from the direction of the angular momentum by just a few degrees, you get several % more error on the Hubble constant. So there's also fundamental things we don't understand about these systems.
Yeah, just to say the LVK is, the scope of the LVK is to give the best constraints using only gravitational waves and possibly galaxy catalogs. And let's say without relying on modeling that is not on our control. That's why our results might be a bit broader than other results in the literature. That is because we are considering this kind of approach.
We can take one last very quick question, if there is. Yeah.
So I wasn't aware of the paper you're referring to, but this mismatch between direction of the GRB and orbital angular momentum would be due to spins, presumably the spins of the objects. And wouldn't neutron stars then have to have fairly large spins? Or I don't have a good picture in my mind, maybe not.
Thank you. Great question. So sure, spin could be an obvious and sort of an obvious factor at play that determines the sort of the direction of the jet. But then the other thing is also, like we've been talking about jets and electromagnetic fields, magnetic fields earlier this week also. So it could also be there's a priori no really good reason of why like a magnetic jet should be perfectly aligned with the orbital angular momentum axis. So there could be intrinsic, MHD dynamo effects that actually, turn out to produce a jet that's not perfectly aligned.
Let's thank once again Nicolas.